你真的知道物体是怎么进行运动的吗？今天我将在10分钟以内教你怎么用微积分解高一下物理物体的运动的题目。So a few days ago, on my school's midterm exam, we had a unit in the physics portion about the movement in kinematic objects. It contained laws like motion, velocity, and acceleration. We had to memorize a variety of different formulas for route length, velocity, average velocity, and so on. But I quickly found a trick to making these formulas link together and easier to understand. You won't believe what it is. I used calculus to do it.
What the? 我信你个鬼!
I know, you're shocked. In today's video, I'm going to make a full analysis on how these physics problems were solved using calculus, and hopefully you'll see how essential it is in the topic of motion physics. Here we go! First off, you've learned in elementary school that distance equals velocity times time. Later on in junior high, you will learn that average velocity is the change in distance divided by the change in time. But what about instantaneous velocity? Well, consider a function s of t, where s is the position axis and t is the time axis. Put 2 points on the t-axis. The corresponding s values will be s1 and s2. Delta s over delta t would look like this. Now, connect the 2 points into a line, and the slope will be delta s divided by delta t. Then, move t2 closer and closer to t1, and you'll find s2 getting closer to s1. Therefore, the change in position, delta s, and the change in time, delta t, would approach 0. And this line will approach the tangent line of s of t at t equals t1. So what's the slope now? This is the main idea of the derivative, and is super useful in motion physics. The slope is now precisely the derivative of s of t at t1, which can be represented as s prime of t1 or ds over dt, and it is the instantaneous velocity at t1. Finally, we can conclude that the velocity can be solved by taking the derivative of the position function. In the same logic, acceleration is defined to be the change in velocity divided by the change in time. Changing the vertical axis to represent velocity with respect to time, we've shown that instantaneous acceleration can be solved by taking the derivative of the velocity function. But what if the velocity is already given, and it asks you to solve the distance traveled between two moments in time? If we're given the velocity function v of t, what is the distance traveled, delta s, from t equals 1 to t equals 5, or from the first second to the 5th second? Well, let's cut this time period into little slices with the same length, delta t. We'll now see a lot of points on the t-axis. Then, map the corresponding vt outputs onto the graph, and they should form rectangles, all of them having the same width. Because the distance is velocity multiplied by the time, the areas of these rectangles will represent the distance traveled within every delta t time period. Now, make delta t smaller and smaller. Notice the widths of these rectangles approach 0, forming more and more of them. Do you see it yet? The sum of these areas will approach the area under the v of t curve from t equals 1 to t equals 5, eventually having no difference. This is the idea of the integral, with the upper and lower bounds being 5 and 1. It can be written as the following. In this notation, dt is the width, vt being the outputs of each point. V of t times dt indicates the area of the rectangles, while the integral sign means the continuous sum of the areas. This is computed by taking the antiderivative of v of t to get s of t, the position function, then evaluating from 1 to 5. We can generalize this changing the 5 and 1 into 2 arbitrary moments in time, and we will end up with the fundamental theorem of calculus part 1. We can conclude that the position function s of t is in fact the integral of the velocity v of t. In the same logic, the velocity function is the same as the integral of the acceleration a of t. As you can see, by using calculus to derive these formulas, we make them not only easier to grasp, but inject it into our everyday lives. If it wasn't for Newton, who invented the idea behind the calculus concepts, motion physics would be much more difficult. In fact, I even consider calculus to be the heart of motion physics, for it's the most direct way to see what's actually going on. Thank you so much, Newton. Well, what about you? What are your thoughts for today's video? Please share them in the comments. I would love to see your opinions. I'll see you later. Peace!